Well, thank you for this award. It's really a great honor, and it's a particular pleasure given all the great friends who are sitting in the audience. So, given the current state of research of AI and multi-agent systems, it is now important to direct this research towards solving societal problems. I'll focus on three: public safety and security, conservation, and public health. In viewing these societal problems as multi-agent systems, there's a key research challenge that can be seen to cut across these problem areas: how to optimize our limited intervention resources when interacting with other agents in these domains. And I'll focus on the use of computational game theory as a solution approach that cuts across these areas. Focusing on public safety and security, we have a large number of targets to protect limited security resources, how to schedule or plan or allocate these resources, taking into account a watchful adversary. We have contributed a new model called Stackelberg Security Games, and contributed new algorithms based on this model that are in use by security agencies in the United States and internationally. With respect to conservation and wildlife protection, we have large conservation areas but limited number of rangers. We've contributed a new model called Green Security Games for optimizing these limited resources. Concrete example is work we have been doing in Uganda, where using past poaching data, we can predict where poachers will set traps. And for the past several years, have been able to remove large number of these traps and even get poachers arrested. This model has been extended towards combating illegal fishing and illegal logging. Third area is public health. Here we have a large population that we wish to inform, but limited number of messengers. A concrete example is work we have been doing with homeless shelters in Los Angeles. Here we have to inform homeless youth about dangers of HIV. We harness the social network of these youth and show that our influence maximization algorithms based on the ideas of games against nature are far more effective in selecting key peer leaders to spread the information compared to traditional approaches. And this work has been extended towards combating other health challenges. In all of this work, partnership with government and non-government organizations is crucial. To that end, we've really patrolled with the US Coast Guard on the boats in New York. Our students have spent time in homeless shelters talking to homeless shelter officials. This immersion is important in order to build the right kinds of models on the basis of which we can develop new multi-agent intervention algorithms. But beyond that, it is also important to really deploy and test these algorithms in the field. This is not only because we want to test the social impact, we want to achieve social impact, but because this field testing and deployment often gives us new insights into what might be wrong with our models and provides us new research directions. So in the rest of the talk, I'm going to talk about the three areas. All of the work I'll discuss has been published in AAA, IAMAS, and ICHCA, and you'll find the relevant papers in the years that I'll give. These papers also provide lots of simulation results. What I'll discuss today are real-world deployment results. All of the work, of course, is thanks to all the great PhD students and postdocs, and to thank them, I'll have their pictures in the top right-hand corners of the slides on which I show their work. So let's start with public safety and security. This is clearly a global challenge. Events of 9/11 were clearly devastating for all of us. 11 July 2006 in Mumbai was particularly challenging for me. Bombs went off on trains in Mumbai. And for several hours, my mother was untraceable. Fortunately, luckily, she got off the train before the bombs went off. But this raised the importance of public safety and security in my mind. So when Chief of Airport Police at LAX Airport, Errol Southers, approached us, trying to improve security at the airport, we were all ears. His concern was someone driving a suicide truck into one of the terminals, as what happened in Glasgow later on. His problem was that there are 8 inbound roads into the airport, 8 terminals, but not enough resources, not enough officers or dogs to be at all terminals on all roads. Our question was, can we use game theory as a way of optimizing the limited security resources? Could we convince the sergeants on the ground? Could we convince the Homeland Security Scientific Advisory Committee? Could we convince our AI reviewers when, in fact, key thought leaders were questioning whether game theory was practically useful at all? But that's what we decided to do, propose game theory for security resource optimization. We proposed a new model called Stackelberg Security Games, which has some two key aspects for tractability. First, it's a security game that is based on a set of targets, whether targets are covered or not. And it's a Stackelberg leader-follower formulation. So let's take a simple example. This is a 2x2 game. We have one defender resource to protect two terminals. If the defender always tries to protect terminal 1, an adversary conducting surveillance will attack terminal 2. The adversary gets a positive reward 1. The defender gets a negative reward -1. In fact, any deterministic strategy the adversary could defeat. If the police were to use a mixed strategy, a randomized strategy, 60% of the time they're at terminal 1 and 40% at terminal 2, then an adversary conducting surveillance will only know that the police are there 60%, here 40%. What they'll do tomorrow remains unpredictable. These kinds of games are called Stackelberg games because the defender commits first to a randomized strategy, and then the adversary responds. We are optimizing the use of limited resources. We are not guaranteeing 100% security because in the real world, there is no such thing. We are increasing the cost and uncertainty to an adversary in coming up with a plan of attack. The challenge, of course, is how to solve massive scale games. So this is how we built the armor system at the LAX airport. We start with a game matrix that's fed into a mixed integer program which produces mixed defender strategies. So probability, there's a K9 patrol at 8 a.m. at terminals 2, 5, and 6 is 0.17. Probability, there's a K9 patrol at 8 a.m. at terminals 3, 5, and 7 is 0.33, and so on. And then we sample from this distribution to generate an actual schedule. So at 8 a.m., send team 1 to terminal 2, team 3 to terminal 5, team 5 to terminal 6. At 9 a.m., do something different, and so on. Now let's look at how we generate the mixed integer program. We are maximizing the defender expected utility. Here, Rij refers to the reward to the defender if the defender were to take a strategy I and the adversary were to take a strategy J. Xi is the probability with which the defender takes a strategy I. For example, X1 is the probability there's a dog on terminal 1 and a dog on terminal 2. X2 is the probability there's a dog on terminal 2 and a dog on terminal 3. In fact, we generate every possible allocation of defender resources to targets and assign a probability variable for that, which was adequate for this application but doesn't scale up, as I'll come to later. Qj refers to the adversary's response, and we ensure that it's the adversary's best response, maximizing adversary expected utility. Let's look at where the payoffs come from. So the threat at LAX was somebody driving a suicide truck into one of the terminals. The loss to the defender would be the loss of human lives that would occur if such an event were to be successful. We had from the airport detailed numbers on how many people were present at different terminals at different times of day, and that's how we could generate a payoff matrix. Later on, I'm going to talk to you about the work we did with the US Coast Guard. There, a team of risk analysts has gone to every single port in the United States for every single target, for every method of attack they have, how many people would be estimated to die, and what would be the economic consequences. So it's based on that that we can generate a payoff. In fact, these estimates are not perfect, we understand that, so we need to be able to handle uncertainty. I'll come to that a little bit later on. But with all of this at work, Armor was operational at LAX. And it turned out to be the first application of using computational game theory for operational day-to-day security. Soon there was news in the local market, TV market. So you could see, people talking about weapons being captured at the airport and lots of guns being captured at the airport. And the LAX police were clearly satisfied, very happy with this. In fact, someone at City Hall was obviously very happy because we received commendations from the city of Los Angeles. Until that point, we had been fortunate enough to have received Best Paper awards from our conferences, and we were very thrilled with that. But this was a really great honor. Errol even went to Congress to talk about our work.
LAX is safer today than it was 18 months ago. A team of research led by Dr. Milind Tambe worked with our department to develop Armor. This software randomizes our vehicle checkpoints along airport access roads and the deployment of our explosives detection canine teams throughout the airport.
So given this congressional hearing and so forth, there was news media. Newsweek said that armor throws a digital cloak of invisibility, which at the next AMAS conference got my friends to ask me if we were working on a cloaking device. But this got the attention of the Federal Air Marshal Service. This is from our first visit to the Freedom Center, home of the Federal Air Marshals. Right at the entrance is the memorial to 9/11 victims. Rubble from the Pentagon, rubble from the World Trade Center, pieces of the plane that crashed into the World Trade Center. And so we were really motivated. Whatever happens, we're going to really try and see what we can do for the air marshals. Their challenge was how to assign air marshals to flights. With thousands of flights a day, the problem was easily of the size 10 to the power 41 defender strategies. If you feed this input into armor, it quietly dies running out of memory. So we needed a different approach to scale up. So let's look at why this problem is hard to scale up. If you look at this game in the normal form, along the rows are all possible defender strategies. We can assign air marshals to flights 1, 2, 3, 1, 3, 5, etc., etc. The adversary could attack flight 1, flight 2, flight 1000. There's 10 to the power 41 rows because there's 10 to the power 41 different combinations, which means there are 10 to the power 41 different xi variables in our mixed integer program, which means this program cannot run. It cannot run, but if we could make it run, what we would find is that most of these xi variables are 0. Our support set size is small. In fact, we can prove that a security game with t-targets, we can obtain a solution where the support set size is t plus 1. So solutions exist where a lot of these xi variables are going to be 0. If we could magically know which those are and remove them from the game matrix, we would get a smaller game matrix, which if we would solve, we would get the exact same solution as we would the larger game matrix. So it's based on this idea that we came up with a new exact algorithm for scale-up based on this incremental strategy generation. So it's the first of its kind algorithm for Stackelberg, specialized for these Stackelberg security games. We start with the master problem with a small number of pure strategies, and there's a slave problem using LP duality theory is going to add the next best pure strategy, and we iterate in this fashion until we converge. This convergence is to a global optimal, but here we only have 1,000 defender strategies instead of the 10 to the power 41. This is the way in which IRIS was built in order to assign air marshals to flights. If you've been on a US air carrier, whether there was an air marshal or not on your flight internationally may have been decided by this program. We were honored to have our work again mentioned in the United States Congress and receive a certificate of appreciation from the Federal Air Marshals. So now I have talked to you about one particular approach to scale up, incremental strategy generation. But soon it was clear that we needed to scale up security games even more. 26th of November 2008, Mumbai was attacked. This is the Taj Hotel on fire. This is just a couple blocks away from where I grew up. In response, the Mumbai police started setting up randomized checkpoints throughout the city. This is a network security game. If you look at the whole map of Mumbai, and if you just look at the southern tip, then in this, we have 150 edges in this network. If you have 2 defender checkpoints, that's 150 choose 2 defender strategies, and all the adversary strategies are all the possible paths the adversaries could take in this network. Of course, in reality, there's more than 20,000 or more road segments, and even with 15 checkpoints, the problem becomes extremely difficult to solve. Here we came up with a new exact optimal algorithm for scale-up using the ideas of double oracle. It's work done with Vince Konitzer. And so here we have a small game matrix, again initialized with a small number of defender strategies and adversary strategies. And now we solve the game, and the defender oracle provides the next best pure strategy to add defender best response. The adversary oracle provides the next adversary strategy to add adversary best response. We iterate in this fashion, grow the game, again converge to a global optimal, and this convergence is fairly quick. So we can solve these large-scale games in under 20 minutes, and this is how, with solving these games and all the other work we had done in security games, I was honored to be invited at the Indian National Police Academy to speak in front of all the senior police officers. These are inspector generals of police and deputy inspector generals from many of India's states. And 2 AI professors who spoke before me were interrupted repeatedly and told that their work was not practical. So when I got up, I was a little nervous about how this was going to go. When I started talking about the checkpoints in Mumbai, this police officer got up and he said, "Milind, I was there at those checkpoints at that night. I chased the terrorists into the Taj Hotel. I actually fought a gun battle with the terrorists. And I thought, this is a good signal. Maybe I should take my double oracles, the NP hardness proof, pack them in my bag, and fly back to Los Angeles. But he actually liked the work. He thought this was great. And this is the kind of collaboration that we are going to pursue in this fall when we spend more time in India. In the United States, in the meanwhile, the Coast Guard had come to us to improve patrolling in different ports. For them, we built this system called Protect. Protect is an acronym, so you can see that we spend enormous amounts of time coming up with good acronyms. So this security game system was developed, but one very interesting new challenge they developed for us was protecting moving targets. This is patrolling around the Staten Island ferry. We developed completely new patrolling strategies that changed the way the Coast Guard used to run patrols around this ferry. Now I'm going to talk to you about how we generated these patrols, and here is a new approach to scale up called marginal strategies. I'm going to use a transition graph representation using discrete space and time. So we have 3 locations, A, B, and C, and 3 time points, 5 minutes, 10 minutes, and 15 minutes. The dashed edges show the way in which a boat could travel within this graph. For example, the ferry can go from C at 5 minutes to B at 10 minutes to A at 15 minutes. That's the green line. The patroller here starts from B, goes to C, and goes back to B. The patroller protects the ferry right next to it. In fact, the patroller can take many of these different paths, red or brown. And now we have a problem just like with armor. To determine the probability of each route, we can solve the armor-style linear program. Except that now we have n to the power t variables, n being the number of locations, t being the total number of time points, so that's how many routes you have. But instead of taking routes as variables, if we take marginal probabilities over segments as variables, we can scale up. Let's take the brown and the red segment here, combine them together into a single probability flow variable. Let's take these 2 brown segments together, combine them together into a single probability flow variable. Now we have n squared multiplied by t variables, and we can show that this marginal representation does not lose any solution quality, and in fact, we can extract back the probabilities that we want. This representation can be extended towards continuous time, and so with this, the Coast Guard were very thrilled with all the results that were given to them. We were honored to receive commendations from the US Coast Guard in their Atlantic area headquarters, and really honored to again have our work mentioned in the United States Congress.
We're working with the University of Southern California to utilize game theory as a way of optimizing and scheduling our patrol. Makes it harder for somebody to anticipate where the patrols will be.
So we then extended this towards many other applications, patrolling on trains in Los Angeles, again using the transition graph representation. But deployment here revealed a completely new, interesting challenge. We want the inspector to leave station B and go to station C with a probability of 0.3, but the inspector may end up having to arrest somebody at station B. So they remain behind with some small probability. To deal with this uncertainty, we encode the defender policies as MDP policies. Here's one way to deal with execution uncertainty. But execution uncertainty is only one kind of uncertainty. There are many other kinds of uncertainties in security games. We have spent enormous amounts of time trying to handle these uncertainties. I'm going to just highlight one paper from AAAI 2014. And this is work looking at minimax regret. So here we are looking at the adversary uncertainty shown as an interval over the payoffs of the adversary. Now, if we think about regret here, if we take one particular payoff instance and suppose that the defender covers target 1 with a probability of 0.3 and target 2 with a probability of 0.7, then the defender's utility here would be minus 2.3. The optimal utility is 0.4. And so the regret for the defender, given this payoff instance, given this particular strategy, is 2.7. Of course, we want to minimize the defender's maximum regret over the entire payoff interval of uncertainty. And so we want to find that strategy which minimizes maximum regret, which means that we have infinite number of regret constraints. To handle this, we can develop a new iterative algorithm, a master problem that generates a lower bound by solving a relaxed minimax regret problem with a small set of attacker payoffs, and a slave problem that computes an upper bound by giving us that payoff which would maximize regret. And when the lower bound and upper bounds converge, we get our optimal solution. Today, we are absolutely thrilled to see the amount of work that's gone on. We saw a whole session just yesterday at Ichigai on security games. We've seen a mushrooming of many different applications in different parts of the world. And the ones in Africa relate to protecting wildlife, and I'll come to that in a minute. But before that, let me just talk a little bit about evaluating these systems. The question we ask here is, how well have we optimized the use of limited resources? And our claim is that security games are superior to optimizing these resources compared to human schedulers or other traditional approaches. And we've done lots of lab evaluations, scheduling competitions in the field evaluations, economic cost-benefit analysis, and so on. Let me just go through a few. So these are patrols done before Protect in Boston. Along the x-axis are different days of the week. Along the y-axis is how frequently a boat visited a particular target. The top green line, for example, is how frequently the boat visited a target on day 1, on day 2, on day 3, etc. So what you see here, there's very few patrols on day 2, a great day to attack the port of Boston. All these lines crisscross, meaning sometimes a target is more important, sometimes next day it's not. But that's not the way. Targets don't change their importance from day to day. After Protect was deployed, you see that the more important targets are visited more, the less important targets are visited less. On any given day where the boat will go remains unpredictable. But on the whole, the more important targets are visited more. And if you look at it from the perspective of Defender expected utility, there is a 350% improvement in Defender expected utility from before to after Protect was deployed. The Federal Air Marshals did a head-to-head comparison playing human against our game theoretic system, and the conclusion was that Iris was just superior. And this is because if you think about a human scheduler, scheduling over 1,000 flights, duty hours, off hours, round trips, risk, randomization for a human being, it is extremely complex, and Iris was just better. We also did scheduling competitions. 90 police officers had to be scheduled on trains in Los Angeles. On the one side was a team of human experts. They took 2 days to generate these patrols. On the other side was our game theoretic system. We had external observers who didn't know who had generated which patrols, standing at different stations, trying to evaluate these patrols over 12 different questions. They graded the game theoretic schedules to be superior. So the humans took a lot more time and actually performed worse. We also went out catching fare evaders on trains, once using our game theoretic system and once using a baseline that was augmented with human experts. This is 21 days of patrol with identical conditions. And conclusion was that the game theoretic system was superior in catching 60% more people traveling without tickets than the baseline system. At the LAX checkpoints, the numbers of arrests from before to after armor grew by 5-fold. So these are just some of the results that indicate to us that security games are superior in optimizing our limited resources compared to traditional approaches. Today, we are pushing this forward. This area in threat screening games, working with the TSA for passenger screening is one big area of work, as well as cybersecurity games. So these are 2 thrusts that we are pushing forward. Let me now turn to conservation and wildlife protection. So before I go on, let's talk about what we are fighting to save. This is Murchison Falls National Park in Uganda, which I visited. There's wonderful wildlife here, but there's threats to wildlife by these traps, these snares. In fact, thousands of wire snares used to kill animals. We have limited numbers of rangers. To optimize the use of these limited security resources, we propose a new model called Green Security Games. Here's Queen Elizabeth National Park in Uganda. We map this into a 1 kilometer by 1 kilometer grid square. Each grid square is a target. Now, we could imagine solving this just like we did before with our mixed integer program, but there is a problem. Here, the adversaries are not fully strategic. Well, it's a problem in that the original program doesn't work as given. What we are dealing with instead are multiple boundedly rational poachers, and so we can't use the best response condition that we had earlier. Instead, we learn the adversary bounded rationality response at each grid location I. So we have given ranger patrol frequency at a location, the features of that cell, and we are trying to predict the probability of finding a snare in that cell. This function GI essentially is giving us the expected utility of executing a certain patrol frequency in that cell. So we are trying to maximize defender expected utility, which is exactly the sum over this function GI. So attention now shifts to learning this function GI. We have 12 years of data from Uganda, from different national parks, and we are trying to predict this probability per square kilometer of finding a snare or this trap. And we have all these features, ranger patrol frequency, animal density, and so forth. There's one complication. When a snare is found, when the rangers report a snare is found, then indeed the snare is found. But when they say that a snare has not been found, it could just be that they didn't walk enough in that grid cell. If they just walked a little bit more, maybe they could have found a snare. So we are sure about our positive instances, but the negative ones we are not so sure about. To handle this, we generate this imperfect crime observation-aware ensemble. The basic idea is to train different classifiers based on different filtered data sets. So this one data set is filtered with patrol effort 1, meaning that if the ranger has walked less than 1 kilometer in this grid cell and reported a negative instance, we remove that negative instance. We don't trust that, and we construct a classifier C1. Another one where the patrol effort is 2 kilometer filtered, meaning that if the ranger has walked less than 2 kilometer and reported a negative, we remove that and construct a new classifier. And now we have a whole range of these classifiers, and we can construct an ensemble. So when we get a test instance where the patrol effort is 1 kilometer, C0 and C1 are used. When we have patrol effort of 2 kilometers, all of our classifiers get used, and so on. Based on these results, we can do tests in our lab. And so look at the data from 2003 to 2015 and say, can we predict well for 2016? Yes, we could. And we could show that it was performing better than competing methods. But this was not enough for our collaborators in Wildlife Conservation Society. They wanted to see actual results on the ground. So we took 2 9-square-kilometer areas in Queen Elizabeth National Park that were infrequently patrolled, were not previous hotspots. So these were 2 areas, green dots, which we are asking them to patrol. They don't overlap with the red dots where snares had been found in the past. And we said, you should patrol here, you're going to find snares. This was done 1 month before ANAMA's deadline, so if snares are found, we have a paper. If snares are not found, there's going to be no paper. So the patrollers went out looking for snares, and first they reported a poached elephant being found. So our system was telling us to go in the right direction, predicting the right kinds of things, except we were too late for this elephant. But then came good news, a whole elephant snare roll. So poachers were active in the area. They were killing elephants, but before they could kill the next set of elephants, we removed this elephant snare roll, potentially saving lives of elephants. And then a whole antelope snare roll was found, and so forth. So our hit rate was higher than the average base hit rate in that period, and so basically this was quite convincing to our partners in Wildlife Conservation Society. One criticism, though, is that this is Uganda. If you find an area in a national park which hadn't been patrolled before, you're going to find snares. So to address this criticism, we ran a second experiment. Here in 2 national parks in Uganda, we predicted 24 areas where we said some of these areas are high-risk areas. So our model predicted some of these areas to be areas where more snares will be found, and other areas to be areas where less snares would be found. These were all infrequently patrolled areas. And now patrollers went out for 6 months looking for snares. So this paper took a very long time to write. In the end, their report where we predicted high, the numbers of snares per patrolled square kilometer was significantly higher than where we predicted to be low. So our predictions were working out very well. In Murchison Falls, we did high, medium, and low. Again, our predictions worked out well. So this is now quite convincing to our collaborators in Wildlife Conservation Society, and we are moving ahead. One area is work we are doing with a non-governmental organization called Air Shepherd. They fly drones in South Africa and take infrared videos. Using deep neural nets, we can then locate poachers and animals in this video, detect them. And the question now, so the software has been built and delivered, and they're testing it, but the question now is to integrate this work within our green security game framework in real time. So that's something that we are pursuing. But even more exciting path forward is work we have been doing with Smart Partnership. This is a partnership of all these different NGOs, WWF, WCS, and so forth, that are taking these green security game algorithms to 600 national parks around the globe, hoping that this would now have a real impact in trying to save wildlife around the globe. And it's not only wildlife, but it's also for protecting forests from illegal logging and illegal fishing and so forth. So let me now come to the third area, which is public health. One big challenge in Los Angeles is the number of homeless youth. We have 6,000 homeless youth who sleep in our streets every night. A big problem is HIV. The rates of HIV amongst homeless youth are 10 times the rate of normal housed population. We have limited resources to spread information about HIV, so the homeless shelters traditionally recruit some peer leaders who are supposed to spread information about HIV in their social networks. This is the traditional problem of influence maximization. We have a social network graph G, and we are trying to choose K peer leaders with the objective of maximizing expected numbers of influence nodes. Now, the assumption here is that we are spreading this information using this independent cascade model. So how this works is that we will inform a peer leader node A, and there's some neighbor of A in this graph, B, and information will spread from A to B with a probability of 0.4, which we know for each edge. In reality, immersion in this domain told us that there's significant amounts of uncertainty. So to model this uncertainty, we can imagine that this probability of propagation is drawn from some probability distribution. And to further model uncertainty, we can say that we are uncertain about the mean of this distribution is drawn from some interval. So now we want to do robust dynamic influence maximization over this uncertain network that we have. And this can be done by casting this problem as a game between our algorithm that is going to choose a policy and nature, which is going to choose parameter values for this propagation to try to cause our policy to perform as worse as possible. The payoffs of this game are the ratio of the performance of the algorithm to optimal values for that particular setting. So this is how the game looks like. We have an influencer that is trying to come up with policies to select peer leaders to spread information, and we have nature trying to choose values for the distribution in order to cause our performance to be as worse as possible. Of course, this game is very, very large because there's lots of policies, lots of parameter settings. But again, we can use our double oracle approach we just talked about in order to solve these large-scale games to reach equilibrium. Now, nature is, of course, sampling from a continuous distribution, but even with that, we can show that we converge with approximation guarantees. But there is a second complication. Our homeless shelters are limited in their resources, so what this means is even though we may want to train 12 peer leaders, we can only get 4 at a time. So we call in 4, and it turns out that one of them got arrested, or one of them can't show up for some other reason. They have difficulties. And so given that, when we bring in the next 4 youth, we need to understand that the last 4 didn't quite work out exactly the way we wanted, so we now have a multi-step policy. So each of our defender policies is this multi-step policy. This problem can be solved by casting it as a POMDP. It turns out that scaling up this POMDP is difficult, and my student Amulya Yadav in his thesis showed clever POMDP partitioning to scale this up. So with all of this, this healer algorithm for robust dynamic influence maximization works. And to test it in the field, we went to homeless shelters in Los Angeles. There are 2 versions of healer, and one baseline, degree centrality, bring in the most popular youth and train them to spread information. In each case, we recruited 60 youth. And now we trained from this, we selected 12 peer leaders from each of these populations. And our colleagues in social work then trained these peer leaders about HIV to spread information. The question is, do our algorithms perform better than the standard baseline of degree centrality? It turns out that Healer and Healer++, our 2 algorithms, are significantly more effective in spreading information compared to traditional approaches. We reached 75% of non-peer leaders, the people we did not bring in, whereas degree centrality just reached about 25%. Okay, so they got more information. Did they actually change behavior? So if you look at what fraction of people who got information actually changed behavior, then with healer versions, we can see 30 to 40% people actually changed behavior and started testing for HIV, whereas with degree centrality, nobody moved around. That's because there's a smaller population to begin with. This has clearly pleased our partners, as you will see.
Beautiful way to kind of like marry this tech world with this social service world, like, and how we can kind of go deeper and impact young people and elevate them.
If this group became a really big thing, it could really help out a lot of youth.
So today we are moving forward with this 900 youth study in Los Angeles. We are working on challenges of suicide prevention and substance abuse prevention. The mayor of Los Angeles recently came to USC and talked about the moral and humanitarian crisis that we are facing with our homeless population. And as an Angelino, I'm really grateful that I can contribute back to my city with the research in AI. On the other side of the world, as a Mumbaiker, I was really honored to be in the audience when Prime Minister Modi talked about AI to a group of AI researchers. He raised challenges of using artificial intelligence for societal benefits. And we are doing our small part by focusing on how we could optimize the use of limited resources to fight tuberculosis, to work on predicting which children may drop out of school and preventing that, optimizing the work of health workers. So that's it. I'm coming to the end of my presentation. I'll say, multi-agent systems research really helps us address complex societal problems. I talked about 3: public safety and security, conservation, and public health. There's a shared multi-agent research challenge that cuts across these areas in terms of optimizing limited intervention resources and a shared solution approach based on computational game theory. I presented several new models, particularly the Stackelberg security game and green security games, and key algorithms, incremental strategy generation, double oracle, and so on. And I talked about the importance of immersion and deployment in order to develop new research challenges. As we go forward, I see a tremendous potential of AI and multi-agent systems research in improving society and fighting social injustice. But for that, it's vital to bring AI to those who have not benefited from AI, for example, the Global South. And we also need to embrace interdisciplinary work with social work and conservation. And here's one last thought. When working on AI for societal benefit, it becomes important for us now to step out of the lab and into the field, not only because we deeply care about societal impact, but because we really need to understand what's the actual societal problem that we're working on, and what are some deficiencies in our model so that we can work on it. And in fact, this is going to be very rewarding because it tells us whole new research directions to follow. So that's it. I want to end by thanking a lot of people, several of whom are in the audience, so many of my friends. I'm really thrilled. I want to start, though, by thanking my mentor, Professor Barbara Gross at Harvard, who has been a tremendous mentor for many, many years. I have so many friends at AMAS. I've written papers with so many, and I see so many people in the audience. I had to somehow limit because there's not enough space on the slide. So I picked those people with whom I had written at least 5 papers in the last 10 years. And so this includes Sarit Kraus, Vince Konitzer, Eugene Vorobechik, Andy Plumtree, not from AMAS, but conservation biology. But again, thank you all who are sitting in the audience here. And my USC collaborators who have been absolutely fantastic: Eric Rice, Bisra Dilkina, Phoebe Villanos, and Fernando Ordonez. So thank you very much. Thank you for listening. And really, it has been it's really a tremendous honor to receive this award. Thank you.
Milind, thanks for this exceptional talk. We are all inspired by your work.
Thank you.
Okay, now let me try to be the devil's advocate.
Please.
I'm a very smart terrorist or poacher. I go to every conference, I read all your papers, I understand everything you do. Can I take advantage of understanding what you do or not?
No, everything is published, but the basic idea that we assume, certainly in the first work that we did with the Stackelberg security games, is that the adversaries know everything. They know the probabilities with which we are covering everything. So it's a Stackelberg model. They are supposed to know everything in the first place. And so as such, there's no advantage to listening to this talk because the assumption is that they know more than what we are presenting even in these conferences. As far as the poachers are concerned, because now we begin to exploit the bounded rationality of these adversaries, certainly there can be an issue if they come to know what is going on and they start poisoning the data by being really smart and corrupt the data. And this is an interesting problem. So we raised it with our collaborators, but they don't think it is so much of an issue right now. Nonetheless, I recognize this is a, $5–10 billion industry to smuggle animal parts from Africa out. And so there's going to be people who are going to try these things out. And so this becomes an interesting area to think about. Not at present a big danger, but something future directed that would be interesting to figure out how to address. Okay. Thank you.
Hi, Milind. Thank you so much for that talk. I'm really inspired by the work you do, and I think this is a really important direction for this community and research as a whole. I was curious also about the distinction you make in the defenders, that in the poaching example, you decided that they were non-strategic, and so you modeled them stochastically, whereas in, like, you know, fare evaders in the LA subway or metro system, you model them as strategic. If I had to guess, I would have thought the other thing would be true because, as you said, poaching is a $5 billion industry. And so that sort of made me think, like, what are the trade-offs between how you model your defenders and how robust are your solutions to mistakes in these modeling choices?
That's a fantastic question, Nicole, and thank you for your kind remarks. With respect to the train domain that we talked about, this is a model as a zero-sum game. So as such, what will happen is that we'll come up with a more conservative solution, so it wouldn't take advantage of the weaknesses of the adversaries as much. And that was in part because we don't have as much data. And by the way, there's also restrictions on what we can get from that data. For example, we cannot say that at a certain station there's more fare evasion going on. That's not ethical. And so it turns out that we need to be very careful about what we can get from that data. And so as a result, this was a more conservative solution that we came up with. In the poaching arena, there's a lot of data that was available, and we went with that, exploiting the fact that we have a bounded rational model that we can use. And certainly the kinds of ethical concerns that had come up in the fare evasion domain were not present in that domain. But it's, you know, the bigger question of how to model, you know, what would be the loss of making wrong assumptions about the adversary, particularly if we move away from perfect rationality. This is a very interesting question, something I think we need to sort of, if we can quantify that in some fashion, I think that would be awesome.
So, thank you, Milind. This is, it's always really nice to see you talk about these things. I think it's really, really important. And one of the questions I have is, what about making sure, how does fairness come into play here? So, for example, in the group, the community leaders problem, I mean, it could be the case, or is there a concern that you keep selecting people that belong to certain communities and thereby marginalizing other people that perhaps just don't have good leaders? I mean, they just don't have people, like, anybody that is able to, they're not good, I don't know, like high degree of vertices, so to speak, and that creates like sub-communities that never get informed or never get access to things, or, well, in the case of security games, you can come up with similar questions.
So thank you. I mean, this is a great question. So I guess the way things work right now, we select these peer leaders, and it turns out there's a secondary effect that we had not anticipated. You know, we talk about biases in AI being very negative. Here, there's something positive. These youth got selected as peer leaders. These were people that homeless shelters and so forth had not paid attention to because they're at the sort of corners of the social network, and the algorithm had picked them up. And they felt this was important recognition. They actually changed their lives. They got better jobs. They had stable housing. So it was a very positive side effect. So now the question becomes, the algorithm is selecting these people. It's really doing it to spread information, but there's a positive side effect that comes off it, this additional benefit. Now, is it fair to pick these people and not others, because now they won't get that additional benefit? So these are kind of very interesting challenges that we had not thought about, and it's, you know, going in the field and sort of looking at what's happening that allows us to recognize that these are some very interesting new issues that we had not thought about. But you're right. I mean, these are things that we need to kind of understand, and this is a very, very new area of work, and something that we would be really delighted to pursue, possibly in collaboration. Thank you.
Sven Zeuthen, University of Zurich. Thank you very much, Milind, for the talk. It's really inspiring. I have a question. If you could say a little bit about how much of the benefit that you've shown comes from optimization and randomization versus the use of game theory?
I think that's a fascinating, fascinating question. So one way to think about it is what would happen if we were to just do uniform randomization, because what game theory gives us is, in a sense, these mixed strategies that are more intelligent and not just uniform random. And so I talked about the baseline, for example, in the train setting, where this was actually a uniform random strategy. That was the baseline against our game theoretic strategy. And because it was so ineffective, the patrollers started getting upset that it was not working well. They were really catching fare evaders in real time. So they would say, I know better where the fare evaders are. I'm going to go catch them. And so even with that addition, it was still performing much worse. So I think there's we have shown this repeatedly, where if you try something very uniformly at random, in the field, it appears not to be effective. And also for the users, it's unacceptable. So by a mistake, because there's a bug in the code, right in the beginning when we were working at our airport, we came up with this uniform random strategy, and immediately there were complaints that this is not working because people are being sent to terminals where there's nobody present. Now, this should happen sometimes, but not all the time. And so there are many reasons to believe that just doing scheduling and then uniform randomization is just not going to cut it. There's another point to take into consideration. When all of this work gets done, we have to present it to scientific advisory committees and so on. And they look at it, and they have their own, they have their own people looking at our work and saying, is this something that should be done or not? And so some of these techniques may not even pass that stage, let alone going into the field and trying things out. There's a much longer answer that I can give as well, but we can discuss this later. But the main point is that we firmly believe that the game theoretic approach improves the situation compared to traditional approaches. In the Coast Guard, for example, in New York, there's very smart people who had been trying out many different optimization techniques by themselves. And we could see that their solutions were not as good as ours because we were able to cover targets much more effectively compared to what they were doing before. So hopefully that gives you an answer, but it's a very, very interesting question and something that needs to, something that we've thought a lot about. Thank you.